All right, good afternoon, everyone. My name is Russ Klein, and I work for Siemens EDA, formerly Mentor Graphics. I work on the high-level synthesis product. I'm with the product marketing team. And my focus over the last couple of years has been using high-level synthesis to generate accelerators, which would make programs running on an embedded processor run faster and use less energy to perform specific functions. And so today I'm going to go over a few of the projects, very briefly a few of the projects that we've worked on where we have taken these accelerators and hooked them into RISC-V processors and talk about the process that we went through there and what our results were. So what we're seeing out in the technology marketplace is that the demand for compute power continues to increase. Video processing, what we're seeing is that the resolutions are still getting higher, 4K and 8K, and the number of frames per second that are being processed is continuing to go up. And so video processing systems have to deal with greater amounts of data. And devices are getting smarter. We're expecting to be able to talk to our device, which means it needs to do voice recognition. And it probably wants to be doing that voice recognition live and on the edge, not sending that up to the cloud somewhere to be processed for the response times. We're also moving more inferencing into the edge. And the inferencing that we're doing is going from billions of floating point operations up into trillions of floating point operations. As we look at networking, 5G is going to increase the amount of data that's flowing through networking systems by a factor of 100. So continuing to see the demands for compute power increase. But in the face of this, scaling, which we've relied on for years to be able to get faster processors and more energy efficient systems, has been decreasing. So Dennard scaling, which was observed by Robert Dennard back in the mid-70s, was that the amount of power consumed by a piece of silicon was proportional to its area, regardless of the size of the transistors. Well, that broke down in the mid-2000s, and as we started to add more and more transistors, we got more and more energy for that same area of silicon, which means we now have an energy problem. Now, Moore's law is continuing. We're seeing the nodes continue to get smaller, but what we're finding is that as we go to the smaller geometries, it's getting more and more expensive to produce those transistors. So on those very small nodes, each transistor costs more and we've got more transistors, which means for a lot of projects that we're working on today, we're not going to get faster, smaller, more efficient transistors. And what that means is that in order to meet the demands for the increased compute power, we're going to have to be more efficient with the transistors that we have. And one way to do this is to take things that are running in software on embedded processors and move them over into hardware. So software has lots of really great capabilities. It is extremely flexible. It is cheap and easy to produce, and we can get software done quickly. And we can also update systems with software typically over the air today. But when we look at it in terms of performance and energy consumption, software is really inefficient. Moving a function into hardware is typically going to improve the overall application performance by 10 to 50x, and the individual function that we're moving by significantly more than that, and reduce the energy at the same time. And also what we're seeing is that in video and 5G and AI applications, the embedded CPUs just don't have enough horsepower to run these applications. They start out in software and they need to end up in hardware. And so the idea is let's push these over into hardware. Now, how does hardware become more efficient than software? Because a multiplier that we put into an accelerator is going to be based on the same silicon, same technology as the multiplier that's in the CPU. And in order to get performance, we need to introduce parallelism. We need to be doing operations at the same time, Within the CPU, we've got a single multiplier, and in even the tightest loop, we're going to see that multiplier get executed maybe 1 out of 6 or 1 out of 8 clocks. In many applications, you're going to see it used a lot less than that. In hardware, we can put a dozen multipliers, and we can run that dozen multipliers on every clock. And so to get performance, we really need to introduce parallelism. And to get efficiency, we really want to tailor the circuit. A CPU will have a 64-bit floating point multiplier. If we put it into hardware and we're dealing with numbers between +1 and -1, we can take a lot of bits out of that floating point multiplier and get a much smaller, more energy efficient implementation. Now, the proposal here is to do this with a technique called high-level synthesis. So what is high-level synthesis? It's an automated path from a C, C++, or System C description of an algorithm. Now, here we have the happy coincidence that most algorithms that we write for embedded processors tend to be C or C++. So with little modification, we can take those to a high-level synthesis tool that will compile up that source, parse it, and create a control data flow graph. That control data flow graph will then get analyzed, and we will create a set of state machines and data path hardware that performs that same function. So it's a compilation process where we end up with synthesizable RTL that does the same thing as that original hardware. And there are knobs within the high-level synthesis tool that will let you target a large but very fast circuit or a small but very energy and area efficient circuit. And you can turn these knobs to specifically target the implementation that you want. So the high-level synthesis tool that I work on is called Catapult. And Catapult does give you architectural control over the design that's being created. So it allows you to introduce parallelism and decide how much parallelism you want to include. And you can control the throughput, the area, and the latency. And you do this by unrolling loops and pipelining activity within the design. It also lets you trade off storage between memories, which are going to be small and efficient, versus registers, which would be fast and expensive. It lets you explore that implementation by changing constraints within the tool rather than going in and changing the source code. It has automatic arithmetic optimizations for bit widths. So in other words, if it can prove that an adder is never going to operate on more than 6 bits, it will lop off it will create an operator that has just that amount, that number of bits. And it also is aware of the target technology that the RTL will be running against. So it is given a technology library for ASICs or an FPGA device where it's targeting an FPGA, and it will know for each AND gate, for each buffer, and so forth, all the combinatorial logic, how much time those take, and is able to insert registers at the appropriate location so that this will just drop through RTL synthesis. And so essentially what we're going to do is take some complex function that's running on a CPU and convert it into a hardware accelerator, and we're going to replace that function in the body of code on the CPU with some interface code that will interact with that accelerator to perform the same function. So our overall software performs the same function. We're just able to do it faster because we're going to be relying on hardware to do some of the heavy lifting. Now, we always want to start with a profile. We want to understand where the bottlenecks are within the software that we're running. And so you're looking for one of two things: a small but often repeated function. So if we have a sequence of 10 or 12 instructions that's just repeated over and over again, we might build that into a new instruction that we'd put into the CPU or make a coprocessor that performed that function. Alternatively, we're looking for really large functions that are consuming 50% or 80% of the total load on the CPU for a particular operation, and move that into a bus-based peripheral. So one of the connections that we did was built an accelerator that would sit on the coprocessor interface for a rocket core. So in this case, we had a program running on the CPU which would pass data to the coprocessor. And this is ideal because it eliminates the traffic on the bus fabric. So all of this data won't be interfering with communication for the rest of the system. It's much faster access than a traditional, than going across the bus. The downside is this accelerator will only be accessed by that one CPU. No other design elements could interact with it. Now, in our implementation, we did not allow the accelerator on the coprocessor interface to go back down to memory because there's some memory consistency issues that you need to be very careful of. So we just avoided that issue and let the Catapult accelerator just hang off the interface. And this is typically going to be used for medium complexity algorithm where the data is tightly coupled with what's going on in software because we won't have to get it out of cached memory. So this might be a filter, an encryption, hashes. There's a wide variety of algorithms that would fit into this. And so essentially what we've got is our processor off here, and then a set of signals to the interface for the coprocessor. And that goes out to a bank of registers, and we'll send operations to write those input registers. And then our synthesized accelerator would sit off on this side and perform the operations. Now, the algorithm that we used was a SHA-256 hashing algorithm. It's performing millions of bit manipulation operations, which general purpose CPUs don't usually do particularly well, but is really straightforward in hardware. And it's also highly parallelizable. And so in this case, we ran this through our high-level synthesis and generated a coprocessor where we were able to run hashes about 25 times faster than the same hashes being calculated on the Rocket core and using about 2% of the energy per hash. So part of that energy savings is the fact that we're performing the operation for a much shorter period of time. Part of it is the fact that we're moving the data around a lot less. Now, our performance was limited by data movement. So in other words, the accelerator went faster than we could pull data in from outside the CPU and pass it across the coprocessor interface. The performance was also dependent on the size of the hash, but still a pretty significant performance increase in energy reduction. The next connection that we made was a slave interface, and this is very similar to what you would do through the coprocessor interface. We're just hanging it off the bus. In this case, it's accessible to any other CPU within the design as well as to other design components. But in this case, we're not going to have it directly reach into memory, which does save us some complexity in terms of caching and virtual to physical memory. And if we have a relatively small amount of computation per data element, setting it up as a slave can actually end up running it faster than having it be a master and reach into memory. It's a little counterintuitive, but we've done some profiling on it and found that to be the case. And so this is, again, for offloading medium complexity computations like we saw before. And so here we're going to have our same register bank, but it's connected through a bus slave. In this case, we did an AXI slave interface. Now, the algorithm that we ran through it was a 2D convolution. So this is out of the TensorFlow library, and it's kind of the workhorse for many AI and image processing applications. And it does dozens to hundreds of operations per pixel that's coming in the feature maps and kernels. It's a very parallelizable algorithm. There's lots of activity that you can do in parallel, very short data dependencies. And the performance is, again, dominated by the data transfer and the size of the images that we're running through. We were able to get a 430x improvement in terms of performance and over 400x in terms of energy reduction. Again, very dependent on the size of what we move through. And I just love this image, so shout out to the towarddatascience.com folks who put this together. This moving GIF really helps folks understand what a 2D convolution is. And so the final accelerator connection type would be a master, where the accelerator itself would sit on the bus. It would be able to master the bus and reach into peripherals or memory and directly read its inputs and drop off its outputs. And in this case, it frees up the CPU so it won't be transferring data. It can go off and do other computations. And so this is really ideal for very large, complex computations that we might want to offload. You do need to worry about cacheable memory and virtual to physical addressing, and make sure that, for example, if you're reaching into cached memory, that everything's been flushed out into the external memory. Typically, you'd move it into device memory of some sort. And your data movement is very quickly going to become your limiting factor. So what we ended up doing, so here we'd have a bus slave as well as a bus master. The bus slave would be for control and synchronization. And so into this, we built an accelerator that was an object detection algorithm. So this was the YOLO Tiny V2 that we did. It's got about 3.4 billion multiply accumulation operations per inference, but it is very highly parallelizable. It does have very large intermediate data sets, so rather than creating memories inside the accelerator, we use the external memory of the system. But because we were able to bring a very large number of multiply accumulate units into the accelerator, we were able to speed this up really dramatically, so over 1,000x in terms of the throughput, and an even greater amount in terms of the energy savings that we got. So this is kind of a summary of all of our examples. So the first one you'll notice is an instruction, and in my agenda, I did have the notion that I was going to do an instruction. We did a B-float operation, which is a brain float 16-bit floating point number that Google put together for inferencing, and built that as an instruction that we've used for other CPU types. We were unable to get this to work in the context of any of the RISC-V cores. It turns out it's actually much easier to add new instructions using Chisel, and so we ended up doing that for an instruction interface. We didn't end up using high-level synthesis. And it was just a matter of bringing an RTL into a Chisel environment. Didn't work very well. The coprocessor, we saw about 25x improvement in performance, 2D convolution, 300 and something, and YOLO Tiny, over 1,000. So these performance numbers do include all of the overhead of moving the data from the processor and the CPU domain out to the accelerator and back, as well as all synchronization and handshaking between the program and the accelerator. And so a couple of observations. One is the larger functions get a bigger performance boost. As we move a bigger and bigger chunk of the software load into an accelerator, we get an even greater increase in performance. Now, the caveat is whatever we're moving has to be parallelizable. We've got to be able to introduce parallelism. Otherwise, we don't get anywhere near the benefit. So that's one thing that you need to keep in mind. The other thing that we observed is that the more specialized the function was, the bigger performance boost we got. So if we left something as programmable and configurable, it tended not to get as big a performance boost. If we hardwired things to specific functions, what we found out is that we got our biggest performance boost. Now, I had a colleague review this presentation last week, and he said to me that there's kind of an elephant in the room. You're going to be talking at the RISC-V conference. People are going to be really well-versed in Chisel. They're probably going to ask the question, why not use Chisel? And my response was, well, high-level synthesis does all of these things that Chisel can't do. And we got into a large philosophical debate, and fundamentally, while I think that high-level synthesis, because it creates a controlled data flow graph and it can analyze that entire graph holistically and be able to do optimizations and implementation in a variety of ways that Chisel normally doesn't, I think there's some advantages here. But his point was, but you could do these things in Chisel. Even though people typically don't, it's still possible. Chisel is based on Scala. Scala is Turing complete, and therefore one could do these things. So I think that my goal here is not to convince you not to use Chisel or that high-level synthesis is an alternative to Chisel. There are a number of things where you've got a big similarity between Chisel and high-level synthesis. So both allow you to raise your level of abstraction so that you're more productive. They both allow faster functional execution of the design, which is necessary. And they both require the skills of a hardware designer to build something useful in hardware. But ultimately, I think they both have their place. And so my goal here is to educate you that this is something that you could do if you've got a particular problem and a skill set that are more suited to Chisel. By all means, you should be using that. So pick the tool that suits the problem and your skill set. So in conclusion, software is really slow and inefficient, and we can no longer rely on scaling to deliver the increases in performance as we used to. Now, moving functions from software into hardware can dramatically improve our performance as well as the efficiency of those functions. High-level synthesis is one of the methods where you can migrate those functions from software into hardware. And because it's using the same language and the same coding styles, it makes it able to do that with minimal changes in effort. All right, so I'd like to thank you for your time today, and if there's any questions or comments, I can take those now.
Yeah, let's get those into the virtual platform. I'll start with an easy one here. In your high-level synthesis, when you're analyzing code snippets to synthesize, is there a limitation to how much code you can analyze? Is there a maximum size, and how would one know what that is going into something like this?
Yeah, there's no hard limit. So the code that you take into high-level synthesis is going to be, as I said, it's turned into a controlled data flow graph, and there's a practical limit where, you know, if we were to take an entire database system or, you know, a very large body of software, that controlled data flow graph would simply be too large to fit in the swap space of the computer, and it simply becomes impractical. And what you'll find is that as you add more and more code, it takes longer and longer to create this controlled data flow graph, and eventually you get to a point where it just doesn't work anymore. But things even as complex as, actually the inferencing algorithm that we did, the object recognition, that was actually a relatively small amount of code, but you know, still billions of computational elements. And so you can do reasonably complex things, but there are limits to the type of code and, of course, the overall size. Okay, any other questions? Yes.
If I understood this correctly, you did not use RoC to perform memory accesses. You switched to the bus master where you connected directly to the fabric. But if my memory is right, RoC does support memory accesses. Why didn't you use those?
RoC does support that, but it does require that the user address all of the memory consistency issues. Right, so when you send data over to the coprocessor and the coprocessor then reaches back into memory, you need to make sure you have as a programmer, have the responsibility for making sure buffers are flushed and that caches are flushed and so forth. And so that was an additional level of complexity that we didn't want to take on in the context of this project. It certainly is doable, and it's something that if we had more time, we probably would have done. Because yes, you're correct that in the RoC interface, the coprocessor can reach out to memory, and it does go through some of the logic within the CPU itself.
Yes.
But it does not get, but you are still responsible for flushing things in, or at least that was what our understanding was as we read the
I
documentation.
don't think so. I think you can use RoC in a mode where it is a full-scale tile link node and participates in the processor cache coherency mechanisms.
So it could arbitrarily ask for any memory location. So given a pointer, it could just go ask for
Yes.
anything, and it would be assured of getting the right value?
Yes.
That's actually good news. We weren't aware of that as we read through the documentation and looked at how it worked. And we had also worked on other coprocessor interfaces, which didn't have such a
Yeah,
thing.
they don't have that. RoC is
Yes.
one of the few that does have that
Yes,
capability.
yes. So our prior work said that that was a big hassle, and we weren't sure that it was fixed over in the RoC side. So we simply didn't do it. And so I wanted to make sure that folks were aware that our numbers reflected the fact that it was the CPU that was doing everything, participating in that. Because certainly you can go much faster if you take advantage of that path. It generates a better implementation. You can move data quite a bit faster.
Okay, thanks.
Thank you. I learned something today. Thank you very much. I appreciate that.
And that's all we have time for, so thank you very much.
All right. Thank you.